All right, ready, guys? Okay, so at this point, we're gonna deal with our probability rules. Okay, so these are our terminologies for probability rules. So we have this notation P of E. And what does it mean? So P of E in here means P means the probability or the chance of occurrence. Okay, of the desired event E. So what you call the E in there is what we call the event or what we call the desired event. Whether it be the winning or the success, or in some cases the losing or the failure, right? Any of those will be what we call our desired event, depending on what the desired event is. In some cases, it will be odd numbers or even numbers, so it depends, right? In some cases, it will be colors. Okay, now, the formula for that one will be the following. It's the ratio between, first, that's N of E. How many unique outcomes are there for the desired event? Okay, so we'll be seeing later, right? How do we count those? So there are different ways of counting those depending on the experiment, okay? It might be like, picking a random, like a colored ball from a box, okay? It might be, getting one card from a standard deck of, poker cards. It depends what the experiment is. By the way, when you say the experiment, that's the play, right? Okay. N of S, that's basically our sample space. In short, how many possible outcomes are there for the experiment itself, right? Whether that be the desired event, the event of failure, right? Or the event of success, summing it all up, then that'll be our sample space, all the possible outcomes. And these are the interpretations of such. If your probability turned out to be 0, what does it mean?
Impossible.
Mason, thank you. Impossible, right? In short, there's no way that this event is going to happen. Okay? Yeah, so if your probability of a certain event is 0, that means it will not happen ever. However, if your probability of event is 1, what does it mean? 3.
Always.
Always, right? No matter what you do, it will always happen. Okay, so that means probability is equal to 1. However, if your probability is more than 1/2, then that means you have a high chance, relatively high chance of that event going to happen. And if your probability is less than half, okay, or 0.5, then relatively, once again, it will happen seldom, right? Rare in some cases. So that will be our interpretations. And the last one is this one, right? Law of large numbers tells us that as the experiment, all right, or the number of repetitions of the trials goes up, right? Okay, so from 100 trials to make it 200 trials, even 1,000 trials, then it will assume that whatever your theoretical probability is, then that definitely is going to happen, okay? So that the probability of an event, theoretical value, you will get it as long as you have experiment trials going up, okay, as it increases. So let us see in here now some cases of what we call our probability event. Let's read this number 6. Okay, yes, Andrew, questions. Yes.
E is the experiment itself.
E in here is the event.
Or the event,
Okay,
sorry,
yeah.
yeah.
The experiment is all, the experiment is the act. Okay, like for example, if you are, let me give you an example, guys. Okay, so ooh, good. Standard deck of cards. Okay, how many cards are there all in all in a standard deck? 52, right? How many colors? 2, right? Black or red? Get it? Okay. How many suits? 4 suits, right? What are those? Spades,
Hearts.
hearts, diamonds, and clubs. Get it? Okay. So 2 colors, 4 suits. Per suit, how many cards for every suit?
13.
For each suit?
13.
13 cards, right? How many number cards per suit? Number cards per suit.
Is it 10?
9, right? 2 to 10. Get it? Okay. How many face cards per suit?
4. 5 again.
Just 3, right? Jack, queen, and king, right? Okay. Ace, sometimes ace is not a number because it's letter A. Not unless it's considered as a number, but I doubt it. Okay, we good? Okay, so ace, 2 to 10, that's 9 number cards. Jack, queen, king are our royalties, or what we call our face cards as well. Are we good? Right. Get it? Okay. Okay. So, what's the sample space? 52. Why? Because there are 52 cards. Get it? Okay. What's the experiment? Picking a card in here is the experiment, right? That's the procedure, right? So, Mason, can you pick a card? Oops, thank you. We good? Right. So, that is the experiment. Get it? Okay. Mason, without looking at the card, what do you want the card to be? You want it to be an ace? You want it to be a jack, a queen, a king? What do you want it to be? King. That is the desired event. Okay. Mason, right? Right? Okay. He wants to be a king. Right? Okay. Get it? Okay. But what did you get?
7 of diamonds.
7 of a diamond, right? So that means that's a failure. Got it, guys? Right? But what is the probability? Unusual. Thank you. Because thank you, Mason. How many kings are there? 4. So that's your N of E, right? There are 4 kings in a standard deck. And what is your sample space? Well, how many cards are there all in all? 52. Get it? So 4 over 52, or 1 over 13, right? In fraction form, is the chance of getting a king. What's the event? Well, Mason said he wants it to be a king. So that's the desired event. Get it? That's his desire, right? That's what he wants, okay? But the experiment is the picking of the card. That's the act. That's the procedure. That's the game. That's the activity. Get it, guys? Questions? But thank you for let's call it volunteering, right? Volunteering okay, for that, what we call experiment, okay? So hopefully you have seen the difference between, but that's a good question. Thank you, Andrew. What's the difference between an experiment and an event? The event is your desired event. Say you want it to be a king, that's the desired event. The experiment is the what? The act of picking a card randomly. Okay? Again, theoretically randomly, okay? Now, let's consider in here number 6. How do we answer this one? Okay, Avi, let's read this one, please. Yes, thank you. Okay, why is the following not a probability model? Okay, so definitely, if you sum up all the events, all in all, it should sum up to how much? 1. Very good, right? So if these are all the events that's gonna happen, right? Either you're gonna pick a red, a green, a blue, a brown, a yellow, or an orange. That is the total number of like what? Possible events, all right, for such. And those are the possible probabilities, okay? So what do? Well, we say that what? That the summation, right, of all the events, right, let's call it EIs, right, the summation of all the probability of the events should be totaling to what? 1, right? Okay, well, let's sum it up. Let's sum it up, right? So how much are these all in all if you add them up all together in your calculator? Let's see what we got, okay? So 0.1, 0.4, 0.2, 0.3. Okay, so let's put it in here. 0.3, so these are 3.1s, right? 0.4, right? Okay. What else? 0.2 and 0.3. Good. Get it, guys? What did we get?
1.2.
1.2. So it's more than 1. Okay, so your probability, the maximum can only be what? 1. Since this exceeds probability of 1, then that means it cannot be a probability model, right? Okay, so once again, the probability of all the events possible should total to 1. Not less than 1, not more than 1, but just 1, right? So in here, since the probability of all the desired events in here turn out to be 1.2, which is more than 1.0, so that means this is what? Not a probability model. Questions, guys? Okay. Now let's read in here, number 10. Let's read number 10 in here and see how we can analyze this, okay? Brett, go ahead, please. In a 7 card.
In a 7-card stud poker, a player is dealt 7 cards. The probability that the player is dealt 2 cards of the same value and 5 other cards of different value, so the player has a pair, is 0.44. Explain what this probability means. If you play a 7-card stud 100 times, will you be dealt a pair exactly 44 times? Why or why not?
What do you think, guys? Right? So again, in a 7-card stud poker, a player is dealt 7. So 7 cards out of how many? 52, right? Okay. The probability that the player is dealt 2 cards of the same value and 5, okay, so 2 cards of the same value. So that means it can be like, say what? 2 cards of the same value. So you say what? 7 of spades and 7 of diamonds, right? So these are 2 different cards, but of the same value. Both are 7, right? So what do we call that on a play? Like a pair or something? Or is there some other? Pair, right? So it's a pair. Thank you. And 5 other cards of different value, so that the player has a pair. Yeah, so just 1 pair and the other 5 are it's 0.44. Explain what this probability means. If you play 7 card stud 100 times, will you be dealt a pair exactly 44 times? Why or why not? So what can you say about this one? So it says in here what? The probability of getting a what? Just 1 pair. Right? Okay. 1 pair out of what? Okay, so the probability of getting a 1 pair out of 7 cards is equal to what? 0.44, right? And we can write it down as what? 44 hundredths. That means in fraction, 44 over 100, right? In short, theoretically, right? Theoretically, every 100 trials in there, right? So again, theoretically, every 100 trials or experiments for this, you will get what? 44 times out of 100. Theoretically, you're gonna get what? 1 pair out of 7 cards. Okay. Now the question is, will you be dealt a pair exactly 44 times? We can say, again, that's theoretically, we can say in here, according to the law of large numbers, if your experiment is large enough, right? Again, if your experiment is large enough, then we can actually assume that that will be the case. That out of 100 trials, each 100 trials, you're gonna get what? 44
Pairs.
times that you're gonna get 1 pair, right? 1 pair in there, right? So with that being said, the question now is 100 trials big enough for that? We can say
yes.
Not too much, right? Not big enough. So we can say, as long as your number of trials is what? I would say more than that, 100 trials, maybe what? 1,000 trials or 10,000 trials, then we can assume that that will be the case, right? But otherwise, there's a risk that that's not gonna be the case yet. Get it, guys? So that's what we call the law of large numbers. And that's basically how casinos are getting profit out of them as well. you must have as many players as possible to actually get a profit out of it, right? Because other than that, there's a risk of like the casino itself or the dealer might be losing much simply because there's not much people actually playing the game. Okay, so the goal is what? To get as many people as possible to play that game. And that's the idea of our lottery tickets as well. Okay? Okay, let's talk about birthdays now. Let's talk about birthdays in here and see how we can work in this one, okay? Birthdays. Let's read these birthdays in here and see how we can work on the probability model for such. Ready, guys? Okay. Juliana, let's read the 28th birthdays. Go ahead, please. Thank you.
Exclude leap years from the following calculations and assume each birthday is equally 20. A. Determine the probability that a randomly selected person has a birthday on the first day of a month. Interpret this probability.
Thank you. All right. So again, in here, you want a what? That your desired event is what? First day of the month. Okay. So with that being said, what's this gonna be? The probability of the birthday as the what? First day of the month will be how much? Well, first, what's your n of desired event? So how many first day of the months are there?
12.
12. Thank you, right? Okay, January 1, Feb 1, March 1, and so on until December 1. So again, there'll be 12 out of what is your sample space? What is your sample space in here? All possible outcomes. In short, how many days are there in a year? 365. Again, excluding leap year. Thank you. Very good. That is correct. 365. Unfortunately, this year is 2024. There are 366 days, by the way. Okay? Right? But again, it says in here excluding leap year. So we exclude this Feb 29. Okay? Yeah, I've just heard the news about like this old lady celebrating her 25th birthday. 25th birthday. So imagine that. 25th birthday times 4. So she's 100 years old, right?
Oh, wow.
Because her birthday is Feb 29. So, okay. So she always celebrates her birthday technically every 4 years. Okay. Thank you. Letter B. Let's read letter B in here. Kalina, go ahead, please.
Determine the probability that a randomly selected person has a birthday on the 31st day of a month. Interpret this probability.
31st day of the month. So still the same, 365 days in a year, but how many? So you know the knuckle counts, right? So I'm seeing some knuckle counts in there, right? So how many 31 are there?
7.
7? What are those days? What are those months? Okay, okay. How do you do that one? January,
And then,
Feb is not, March,
yeah.
April, May, June, July.
Yeah, so that's
August is the same, right?
Yeah.
July and August are both 31,
Uh-huh.
right? And then September, October, November, December, right?
Yeah.
So how many?
7.
1, 2, 3, 4, 5, 6, 7. Okay. Are we good?
Indeed.
Indeed. All right. Okay. Questions regarding that, right? Okay. So, okay. Anyway, it says in here, interpret this probability. What does that mean? 7 over 365, which means what? That for every 365 people that we encounter randomly, right?
Yeah.
Okay. 7 of them, right? There's a chance that 7 of them will have what? their birthday on a what? On a 31. Either January, March, what else? January, March, April. No,
May.
March, May,
And
right?
then July and August.
July, August, what else?
October.
October, thank you, and December. Thank you. And we got it, guys? Okay. Next one, letter C. Let's read letter C here. Giselle, you see letter C? Mhm. So again in here, this is what? 31st day of the month, right? Letter C. Let's color this purple, right? Again, your desired event in here, born in December. So typically, if you're talking about what we call this Western astrology as well, December is what? What sign is it?
Sagittarius.
Sagittarius or Capricorn as well? Is it Capricorn as well? Is it Sagittarius, Capricorn or something? Anyway, if those who are familiar with us, okay, astrology. Anyway, is that Western or Eastern? I think it's Western astrology, right? Okay. Anyway, what is that? Well, out of 365 days, 31. Very good. That is correct. Okay, very good, right? So that is that. Since there are 31 days in December, that is what we mean by that. Okay, so in short, the same, interpret the result. That means what? For every 365 random people that we can ask what their birthdays or when they were born, right? We can notice that 31 out of 365 people will tell us that they were born on the month of December. Questions? Okay, so I'm gonna give you 2 minutes, all right, to consider letter D. Okay, I'll give you 2 minutes to consider letter D and see how you can work on that one. Okay.
I said one.
Yeah, me too.
Yeah.
See, so far this is like the most awesome concept of all semester.
I'm gonna ask him if we're gonna do probability diagrams.
Hey Siri, set timer 2 minutes.
Yeah, for a second I was like, is there 2 November 8th? 2 November 8th.
Oh.
It just felt so easy.
Well, if someone already has the answer, you can share it with the group, all right, with the class, if you want to. Okay. Anyone?
Like, yeah.
Over 365, very good, right? Because there's only one November 8th out of all the 365 days in a year, right? So see, it's not even 2 minutes, okay? Now let's consider some, you know what? It's getting springtime already and summer is near, so we might as well consider some. What's this? Roller coasters. Roller coasters in here. So let's consider these roller coasters in here. See how we can work on this. Number 44, our roller coasters. What's this? Six Flags. Have you been to Six Flags theme park? Good. What Six Flags theme park you've been at?
I think it's the one in Atlanta.
Atlanta. There's one in Atlanta. Very good. There's one in Virginia as well, right? If I'm not mistaken, right? Okay. Anyway, let's read this one in here. Number 44. Liana, go ahead, please. All right. Yeah.
In 2011, Six Flags St. Louis had 10 roller coasters. The Screaming Eagle, The Boss, River King Mine Train, Batman The Ride, Mr. Freeze, Ninja, Tony Hawk's Big Spin, Evil Knievel, Caliber,
Evil Knievel.
and Sky Screamer. Of these, The Boss, The Screaming Eagle, and Evil Knievel are wooden coasters. Ethan wants to ride 2 more roller coasters before leaving the park, not the same one twice, and decides to select them by drawing names from a hat. Determine the sample space of the experiment. That is, list all possible simple random samples of size n equals 2.
Thank you, right? So Ethan, okay, wants to ride, what's this? 2 more roller coasters before leaving the park. Not the same one twice. Not the same one twice. So that means no repetition, right? So when you say not the same one twice, that means that's what? No repetitions. Okay? Yeah. Which means whatever he chose, the first one, he will not repeat it anymore, right? He will choose a different roller coaster. Again, out of those 10. But again, out of those 10, how many are wooden coasters? Let's count. 1, 2, the Boss, Screaming Eagle, and Evil Knievel. So 3 wooden coasters as well. So determine the sample space of the experiment. That is, list all possible simple random outcomes of size n equals 2. So in here, we say what's in here? No repetitions, right? And also in here, we can also say that there is what we call an order for such, right? Is there an order for that? Because it says, wants to ride 2 more roller coasters before leaving the park. Not the same one twice, and decides to select them by drawing names from a hat. Okay, so we can say once again, no repetitions for such. So with that being said, what can we say in here? So we can say in here that the first pick, okay, how many coasters or roller coasters does he have for the first pick? 10, right? So it doesn't matter whether it's wooden or any type of roller coasters, there's 10, right? What about the second pick? So this is the second pick, and I'm gonna put it in here, and so these 2 conditions must be satisfied, right? Well, since you already picked 1 in there, whatever you picked first, that cannot repeat anymore, right? Again, it says no repetitions. With that being said, what do you think is your second pick? How many remaining roller coasters do you have left? 9. Okay. Now what do we do with these 2? This is basically what we call the fundamental counting principle as well, which means that if you have 2 events, all right, or n events independent of each other, then you have to multiply their possible outcomes. So with that being said, how many possible outcomes do we have? 10 times 9? 90 possible outcomes. So this is what we call our sample space. Okay, get it, guys? So once again, the first pick will be how many roller coasters? 10, right? But since whatever you pick first, you cannot repeat that ride anymore. Okay, so you know. Huh?
You call that what?
Fundamental counting principle, right? So let's put it in here. Thank you. Right there, what we call the fundamental counting principle. Again, it basically just tells us that if we have n outcomes independent of each other, to get all of those outcomes all together, we just have to multiply each of their possible outcomes. Okay, so that's what's our what we call n of s, right? Okay. Sample space. Okay, let's now read letter B and how we can answer that one. Letter B. Okay, joining. Let's go ahead. What is the probability? Thank you, right? So what's the probability that Ethan will ride Mr. Freeze? And after that will be Evil Knievel, right? So that'll be what? So the first pick should be what? Mr. Freeze, right? So let's call it F, right? So where's that, Mr. Freeze? Okay. Well, there's only one Mr. Freeze, right? So in here, the first pick is Mr. Freeze, right?
Yeah.
And the second pick is what? Where's that? Evil Knievel, right? So let's color it green, right? So with that, let's make it letter E. Where's that? The Evil Knievel in here. Letter E. So that means in here, the second pick is Evil Knievel. Okay. So let's put it in here, 1 as well, right? Since there are 2 desired events, we're gonna multiply them all together, right? And what is our sample space? 9, right? Okay, so again, our 9 in here is like what? First pick, you have 10 actually roller coasters to pick, right? But on the second pick, whatever you pick first, you cannot pick second anymore. Again, that's what we call no repetitions. That's 90 all in all. Get it? So let's see, what's 1 over 90? Here. Are we good, guys? Questions with that one? Okay, so as you may notice in here, that's 0.011, right? However, we saw a while ago it's 0.022. Why is it the case that we have the 0.022? So here's the deal, okay? So if we go back in here, okay, here we go. Going back, okay. 0.011, and this is 0.022. What happened? It doubled, right? Why do you think it's doubled? So here's the deal. So in here, we just considered in here that the first pick is what? The first pick is Mr. Freeze, and the second pick is Evil Knievel. However, it can be flipped, right? What if you got what? The reverse, right? Okay, in short, what if your first pick is actually the Evil Knievel, and your second pick is actually what? Mr. Freeze. Well, it's just basically the same case, right? That's why in here, we say what? The order is, we consider the order as well, right? So the first is Mr. Freeze, the second is Evil Knievel. However, if you make it what? Well, what if you did Evil Knievel first and then Mr. Freeze the second? It's just the same case. So with that being said, what do we do in here? You multiply it by 2. Are we good, guys? What we did. So that's 0.022. Okay. Considering what? The reverse of that one, right? Okay. What about letter C? Okay, let's read letter C and see how we got this one, okay? Emma, let's read letter C. Probability that Ethan will ride the Screaming Eagle. Screaming Eagle. How many will that be? So there's only one Screaming Eagle, right? So that's the first pick. And then the other ride, or the second ride, will be what? So this is 1S, right? The other ride will be what? Well, how many more options do you have? 9 more options, right? Because if you chose the Screaming Eagle the first, right, then you have 9 other options after that, right? Again, you cannot repeat, so that will be 1. Guys, once again, that is if this is first and that is second. But again, you multiply by 2 because they can flip. Get it, guys? So that means, what if you have this first and that is your second? So that will be the case as well. So you multiply it by 2 as well, and then make it over 9. Okay, so let's see, how much will that be? What's that? 1 times 9 times 2, that's what? 18, right? Over 90, and how much is that? 18 over 90, and do we get a 0.2? Let's see. All right. 18 over 90.
Yeah, they're both a little.
Are we good?
So D was calculating for. Which one did we just do? C or D?
C.
Oh,
Did we do letter C? Yes.
So you're just calculating for the Screaming Eagle, right? Only.
So
Yeah, what is the probability that Ethan will ride the Screaming Eagle? But again, technically the experiment is he will ride 2 coasters, right? So out of the 2 coasters, one of them will be Screaming Eagle. But since you would choose 2 coasters, then the other roller coaster will be what? You have 9 left to choose from. Get it? Thank you guys, and tomorrow we'll continue with our probability of events. Okay?
It will forever never be
two more roller coasters.
Correct.
Not